higher order derivatives. The second derivative, third derivative, fourth derivative, 20th derivative, even the nth derivative of a function. In order to do it, we need to pick up a pattern by finding the first few derivatives and seeing what the pattern of the derivatives holds. Let's look at a few patterns. While these aren't derivatives, it's merely just studying the patterns at the moment. You'll notice in this case that every time the power of x is one more than the value of n. Therefore, when n equals k, we're going to have the power of x one more than the value of n, one more than k, therefore x to the k plus 1. Now, let's have the next one where we're doing much the same thing. We also have x squared, x cubed, x to the 4, but now we have coefficients, numbers multiplying them. So now we need to look at the pattern and say, well, what's happening to these coefficients? Well, they are powers of 2. 2 to the 1, 2. 2 squared, 4. 2 cubed, 8. So thus we're going to have the same x to the k plus 1, but with it we're going to have 2 to the k. And there now is our kth term. Let's take it one step further now. The same sequence again, but this time they're alternating in sign. Notice that the negatives coincide with when n is odd and positives when n is even. Well, that's pretty straightforward then, because a negative to an odd power, such as 1, gives us a negative, such as 3 gives us a negative. Negative to an even power, such as 2, gives us a positive. Thus, we can consider this to be negative 2 to the k times x to the k plus 1. Now we're looking at a different sort of pattern. No longer powers, but now we have 3 to 1, 2, 1, 1. If n was equal to 4, it would be 1 times 2 times 3 times 4. This involves what we call factorial, the exclamation mark. K factorial means k times 1 less than k times 2 less than k, all the way down to times 2 times 1. Let's introduce the alternating sign to it. Notice in this case we have to be careful, because when n is odd, then the term is positive. When n is even, the term is negative. So therefore we have to raise a negative to a power 1 more than or 1 less than n. Thus we have our k factorial again, but we have negative 1 to the k minus 1, so it'll be negative 1 to the 0, negative 1 to the 1, negative 1 squared, or k plus 1, where it'll be negative 1 squared, negative 1 cubed, negative 1 to the 4. Let's have a bit of a look at notation. There's our first derivative. Second derivative, just derivative of the first derivative. Third derivative, derivative of the second derivative. Fourth derivative, fifth derivative. This is going to become a bit tedious, of course, because if we have the 50th derivative, we're going to have 50 of these prime signs. Going to be a bit much, I think. So we go on to a different system. 1 is fine, 2 is fine, but us mathematicians are lazy, so from 3 upwards, no. We're going to change our system. Instead, we'll put whatever number derivative it is in brackets, written as a superscript. Therefore, fourth derivative, we'll write 4 in brackets at the top there, like that. So let's get on to the first example. f of x equals x cubed, and we have to find the nth derivative of f of x. So we're going to determine the pattern. We're going to write the first 4 terms, you'll see why in a moment, and then we'll write the nth term. Usually we only need to do 3 terms, but this one will need a 4th. First derivative, pretty straightforward. Second derivative, third derivative. When we differentiate 6, we get 0. Every time after this, when we differentiate, we're going to get straight back to 0, so therefore the nth derivative is going to be 0. Of course, strictly speaking, this isn't quite true. It's only true for n greater than 3, because when n is 3 or when n is 2 or when n is 1, we have different values. So either we'd have to say fn of x equals 0 for n greater than 3, and fn of x equals, and we'll have to put a formula for those ones, or state them, because it's a fine number of them. There are only 3. Let's have a look at the next one here now. First 3 terms and the nth. Multiply down by -1, subtract 1 from there, there we are. Now multiply down by -2 and subtract 1 from the -2. Note that I have not multiplied those 2 terms together. Once you multiply them together, then the pattern becomes hidden. You have to keep them separate. So therefore we have it like that. Now there are 2 things to consider. First of all, what the sign of them is. This is going to be negative. This is going to be positive. This is going to be negative. In other words, it's alternating. Negative when n is odd, positive when n is even. So that's where that -1 to the n will come in. Then of course we have factorials. There we are. N is 3, it's 3 factorial. So that's pretty straightforward. These powers of x are related to n when n is 1, -2, when n is 2, -3, when n is 3, -4. That's a linear sequence. Common first difference sequence, which at this stage you should be pretty experienced at doing and finding a formula for. Therefore our formula overall is going to be -1 to the n, that allows for the changing in sign, n factorial, and then x, the -n minus 1. Let's just confirm that. When n is 1, -1 minus 1 is -2. When n is 3, -3 minus 1 is -4. So it works. Let's look at a slightly more complicated question. Notice this one we're going to have to differentiate by chain rule, because we have a function g of x equals 2x minus 3 inside a function which is 3u to the -5. So every time we have to differentiate the outside function and we have to differentiate the inside function. First derivative, 3, their -5 multiplies down, there it is, times 2x minus 3 stays the same because that's the inside function, to the -6, drops 1 off there. But now we have to multiply by the derivative of the inside function, which is 2. Here it is. Once again, we're not going to simplify that because we'll lose the pattern. Second derivative. Here it is. Notice that we've got there, we've multiplied down by -6, so there we are. 2x minus 3, same inside function, to the -7 times 2, and then we've had to multiply again by the derivative of the inside function. So there it is. Third derivative. Multiply down by the -7. 2x minus 3 stays the same. Subtract 1 off the -7. And multiply by 2 the derivative of the inside function, which just combines with those first 2 2's, giving you that. Now let's see what sort of patterns we have at this stage. First of all, we have alternating sign. Secondly, we have almost what looks like a factorial, We have a 333 there, which is constant. Then we have a 765, 655. Right, so in fact it's like a 7 factorial but without the 4321. Well, we can do that. 7 factorial, we divide by 4 factorial because that cancels out the 4321. To go by the pattern, I'd go to look at that as 3 plus 4 because the 7 factorial is when n is 3. And I'll say, how do we get 7 from n equals 3? Oh, we add 4 on. How do we get 6 when n is 2? We add 4 on. How do we get 5 when n is 1? We add 4 on. So there we are, 3 plus 4 factorial. And there's the alternating sign. So we have to allow for that too. Then we also have to allow for that when n is 2, when n is 1, you get 2 to the 1. When n is 2, you have 2 squared. When n is 3, you have 2 cubed. Then we also have to look at when n is 1, we have minus 6 as the exponent, n is 2 is minus 7, n is 3 is minus 8. Once again, we have ourselves a linear sequence, a common first difference sequence. So there's our final result. The 3, there it is. Alternating in sign, therefore negative 1 to the n. Because it's negative when n is 1, then we go straight for negative 1 to the n. We don't worry about n plus 1 or n minus 1. N plus 4, well there we are, 3 plus 4, and remember the n was the 3. Factorial all over 4 factorial. Times the inside function, like that, minus k minus 5. That is the linear sequence that arises from when n is 1 you get minus 6, when n is 2 minus 7, n 3 minus 8. And then of course times 2 to the n. Right, let's have a bit of a side order, a new term, modulo. Some may have come across it in physics. Another term for it is modulus. If we say 33 modulo 5, we mean the remainder when 33 is divided by 5. So 33 divided by 5, 6 5s are 30, remainder 3. And there we are, there's modulo 33 modulo 5. The way we're going to write it is as it's done in Excel, with an equal sign obviously in Excel. Mod 33.5, and the same in most computer programs. That means 33 divided by 5. What's the remainder? Let's take some examples. Mod 16.3. Well, 16 divided by 3. 5 3s are 15. Remainder 1. Mod 49. 40 divided by 9. Well, 4 9s are 36. Remainder 4. Mod 65, 11. Well, 5 11s are 55, remainder 10. Now, where we're going to use this modulo is in this sort of function, because this is a repetitive derivative. Let's consider the derivatives. Once again, I'm going to go to the fourth derivative. You'll see why. Right, the derivative of sine is cos. Derivative of cos is minus sine. Derivative of sine is cos, and we must keep in mind the negative's already there, so therefore negative cos. Derivative of cos is negative sine, and there's already a negative, so two negatives make a positive sine. Now here's the pattern. Cos minus cos sine. Fifth derivative will be cos. Then you'll get minus sine, minus cos sine, cos, minus cos sine. So notice that it's cos when n is 1, when n is 5, when n is 9, one more than any multiples of 4. There's your modulo. N4 equals 1. It's minus sine when n is 2, when n is 6, when n is 10. In other words, 2 and then every fourth. So in other words, if you take n, divide by 4, we're interested in the remainder. 2 divided by 4, remainder 2. 6 divided by 4, remainder 2, etc. Now we're also going to use what's called a piecewise defined function because there are 4 different answers depending on the values of n. So we're going to come up with that. Cos x when mod n4 equals 1. In other words, when n is 1, 5, 9. Mod n4 equals 2 when n is 2, 6, 10, etc. When mod n4 equals 3 when n is 3, 7, 11, etc. And mod n4 equals 0, in other words, when n is 4, 8, 12, etc. And there is our pattern. Here's the reminder. Mod nk is modulo nk, where modulo is the remainder when n is divided by k. Mod 25, 7 is 4, because 7 to 25 gives you 3, remainder 4, and the 4 is the modulo.